All right, this video is just question 13 out of your notes. It's still partial pressures, but now we're taking into account something called mole fraction with it, which is just what it sounds like. It's just the fraction of moles in a container. So remember, partial pressures, if we have a mixture of gases, the total pressure is equal to the partial pressure of each gas. Okay, so I've got a mixture of gas over here, in a container. 5 moles of oxygen, 3 moles of hydrogen, 2 moles of CO2 in the same container mixed together. So assuming that there's no reaction taking place, they're just staying mixed in that ratio. Oxygen would be causing the most pressure because it's the most moles. They're at the same temperature and in the same volume because they're in the same container. This would be the next most pressure. That would be the least pressure. Okay, whichever one has the more moles is causing more pressure because there's more molecules of that hidden in the container. If I wanted to figure out the mole fraction of those gases. Okay, so mole fraction, which is symbolized as an X. That seems weird, but X is called the mole fraction. If I want to know the mole fraction of, say, oxygen, I would take the moles of oxygen divided by the total moles in the container. Well, 5 plus 3 is 8 plus 2 is 10. 10 total moles. So the mole fraction of oxygen is 0.5. In other words, 50% of the moles are oxygen. That also means then that 50% of the pressure is oxygen. Okay. So the mole fraction of oxygen would be 0.5. For hydrogen, it would be 3 out of 10 moles. So the mole fraction of hydrogen would be 0.3, and for CO2 it would be 0.2. If the total pressure in here was, let's say the total pressure in here was 5 atmospheres of pressure. Well, half of that pressure, because the mole fraction is 0.5, half of that pressure would be from oxygen. So 2.5 atmospheres would be from oxygen. 0.3 is the mole fraction of hydrogen. So 0.3, in other words, that's 30%. 0.3 times 5, which would be 1.5 atmospheres would be hydrogen. And then this mole fraction would be 0.2 times 5 would be 1 atmosphere. Okay, so the total pressure would add up to 5 in that case. 2.5 atmospheres for this, 1.5 atmospheres of that, and 1 atmosphere of that would total up to 5 atmospheres. So we can use mole fraction to figure out the partial pressure of a gas or of gases in a container. So this question is telling you have this much hydrogen. It's collected by water displacement. Remember, that means collected over water, so it's a wet gas. That means you have the gas and water vapor pressure at 25 degrees Celsius. The vapor pressure of water at 25 degrees Celsius off of a chart is 23.76 millimeters of mercury. The total pressure for this container is 647. Wants to know the mole fraction of hydrogen and water in the gas mixture. Okay. So remember, our total pressure is the water pressure plus hydrogen. So I just subtracted 647 minus that and got hydrogen. Obviously, the pressure for this is a lot more, so it must have a much higher number of moles and a much higher mole fraction. Okay, so a couple of ways we could do this, actually. If we go back to this one, again, we said that the total pressure in here was 5 atmospheres. I said that this one was 2.5 atmospheres. 1.5 atmospheres. I did that wrong, didn't I? No, that's 4. And 1 atmosphere. Well, I can get mole fraction. So moles and atmospheres are kind of synonymous. I can get mole fraction by taking moles out of total moles, or I can do pressure out of total pressure. For example, oxygen was 5 moles out of 10 total moles, which is 0.5 for a mole fraction. Or I could do 2.5 atmospheres of pressure out of a total of 5 atmospheres of pressure, again, is 0.5. So I can do mole fraction in terms of moles or in terms of atmospheres. I can't mix them together, but I can get my mole fraction based on that, because whichever thing is causing the ratio of them in moles is also the ratio of them in atmospheres if they're in the same container at the same temperature. So in this case, a hard way to do this problem would be to convert this into moles, and get mole fraction from that. An easy way to get the mole fraction would be to just take the pressure. So if I want to get the mole fraction of water, I can take its pressure, 23.76, divided by the total, 647. If I want to get the mole fraction of hydrogen, I can take 623.24 over the total pressure, 647. Okay, so I get the mole fraction in that way. The mole fraction of hydrogen is 0.963. Well, the total mole fraction has to add to 1. If the mole, we're saying it's a fraction of the container, so if I just take 1 minus that number, I can get this one, or divide those two, is about 0.037. So this is causing a lot more of the pressure than that one, obviously. All right, here's maybe a little bit more legitimate question. So this one down here is telling you have a container, and this container contains this many grams of methane, this many grams of neon, and this many grams of SO2. Okay. Now I can't look at these and go, well, this one causes the most pressure. It's whichever one is the most number of moles, not the most number of grams that causes the most pressure. So once I figure out moles, I can figure out which one is causing the most pressure. Okay. It's telling you the temperature is 85 degrees Celsius. It's a 75-liter container. So what I would suggest, first thing I would do is turn each of these into moles. I don't have to do PV equals nRT. I've got grams of them. So I can convert this into moles, this into moles, this into moles. Okay, and get each of those. So divide this one by its molar mass, divide that one by its molar mass, and that one. Okay, I'm not going to show that work. I think you guys can get moles. So here are the moles. This one is 0.361 moles. Neon is 0.108 moles. And SO2 is 0.106 moles. So I could get my mole fraction here fairly easily if I wanted to. So let's do that. So if we add up the total number of moles, that plus that plus that, our moles total are 0.575 moles. So if I want to get the mole fraction of each one, divide this one by 0.575, divide this one by 0.575, so I can get my mole fraction for each of them. This one is 0.628. There's no label for mole fraction. It's really, it's really a percent. We're saying 62.8% of the moles are that. This one is 0.041, and this one is 0.188. So those are the mole fractions. Again, that's methane, neon, and SO2. So obviously this one is causing most of the pressure. Second most, the least pressure is caused by the Ne, because that's the least number of moles. So again, I need to know what is the total pressure in this container and what is the partial pressure of each gas. Well, if I want to get the total pressure, I can go PV equals nRT. Okay, now I could plug in any of these moles individually and get pressures, if I wanted to do that. Or I can plug in the total moles and get the total pressure of this container, and then use the mole fraction to see what each pressure is individually. Okay, so if I plug in 0.575 moles, so I can go P times 75 liters equals 0.575 moles. That's the total moles of gas. So I'm finding total pressure. Whatever you put in here for moles is what you're finding pressure on. If it was moles of just CH4, it'd be that pressure. 0.0821. And temperature is 85, which would be 358 Kelvin. When you solve for that, you get 0.225 atmospheres. Had pretty small amounts of moles. So that's why it's such a small pressure in a 75-liter container, so a big container too. So not much pressure in there, there's not much gas. So now if I want to know which thing is causing the most pressure, I can take 0.628 times that. So I'm going to write that up here. So I want to know the pressure of CH4. I'm taking its mole fraction, that's the X, times the total pressure. Well, CH4's mole fraction is 0.628 times the total pressure was 0.225 atmospheres. The pressure of CH4 is 0.141 atmospheres. Do the same thing here with neon. Take 0.041 times that number, and then that one times that number. Again, our pressure should add up to 0.225, but when you get down here, neon's pressure ends up being 0.041 atmospheres. Oh. Don't think I have that right. I think it's 0.042 atmospheres for neon. I do not have the other one. For some reason I have not done those, but you could add those together. You know, this plus this, subtract that out, would be your pressure of whatever's left over there. So again, total pressure is the pressure of each gas. I'm going to do one more thing here that's not on your sheet. A stoichiometry question with this same information. I'll make this kind of quick here. So again, this is not in your notes. So I'm giving you an equation here. So you have ammonia gas reacting with oxygen gas. It's in a 4 to 5 ratio, producing nitrogen monoxide gas and water vapor. Okay, so everything is a gas in there. It's telling us we used 80 grams. We're using 80 grams of NH3. Okay, it's not a limiting reactant question, although I will give you one at some point here that is. So we're going to say we have the exact amount of oxygen we need, no excess, okay, and not anything short. And I want to know at the end, what is the total pressure and the partial pressure of each gas over here. Okay? And they're collecting these two gases. So they're collecting these two gases in a 5-liter container. 5-liter container at 100 degrees Celsius. 5-liter container at 100 degrees Celsius. Obviously, water is going to cause more pressure than NO. There's going to be more moles of water than there is of nitrogen monoxide. So we'll do our stoichiometry. We got 80 grams of NH3, 17 grams is a mole of ammonia. So here's where I'm going to do something a little different from what we've typically done. I'm going to say that for every 4 moles of ammonia, there's 4 plus 6, there's 10 total moles of gas produced in this reaction. I could do each one individually, but I can just say for every 4 moles of this that are used, it produces 10 moles of gas at the end of the reaction. So I just want to know how many moles of gas are made at the end of the reaction. When I do that, sorry, my answers are over here, I get 11.76 moles of gas. Obviously, more of those moles are water than nitrogen monoxide. So now I want to know the pressure. So I can get the total pressure and each individual pressure. Okay. I could have solved for each gas and PV equals nRT twice. I'm just going to do PV equals nRT once using 11.76. So I'm going to go, trying to figure out our pressure total. Volume, our container is a 5-liter container using the 11.76. So that's, again, total moles. 0.0821, 373 because it's 100 degrees Celsius. So we're going to solve for the total pressure there of all of them. I think it is 72 atmospheres, I remember right. It is. Okay, so it ends up being 72 atmospheres of pressure. Okay, 72 atmospheres of pressure. That's total. Okay, so that's one thing I wanted to know. So in this container, these two gases are causing 72 atmospheres of pressure. Well, I can get the mole fraction of them very easily. there's 4 moles of this out of 10 total. So the mole fraction of NO, there's 4 moles of it out of 10 total moles. Okay? All we need to know is it's just that ratio. In other words, the mole fraction is 0.4. It's always that. It's always 4/10 of the moles, 40% of them. So if I take 0.4 times 72, that would tell me the pressure of NO. And then take 0.6, mole fraction of water, would be 6 out of 10, 0.6. So take that times 72 would be the partial pressure of the water vapor. It ends up being like 28, something like that. Actually, I guess, yeah, 28.8. So NO would be 28.8 atmospheres, and then whatever's left over, 72 minus that, so like 43 point something. Okay, 43.2 atmospheres would be the water vapor.